Okay, today we are going to talk about another conic section, and this conic section is called the ellipse. The ellipse is basically an oval, except it's a special mathematical oval that has a definition, okay? So we talked about the circle being the set of points equal distance from a single point, the parabola being a set of points equal distance from a point and a line, the focus and directrix. When I add those two distances, they're the same. An ellipse is a set of points where the sum of the two distances from 2 points is equal. And then we'll talk about a hyperbola tomorrow, which is the difference of the distance from 2 points. So with an ellipse, here I've got all these distances have to be constant. So I'm labeling the distances. C plus D, that's got to be equal to A plus B which is equal to E plus F. Any of these distances. Let's do one more. G and H. So sum of my distances is equal. Okay. That's the definition of an ellipse. Okay. The next thing I'm going to do is tell you the equation for an ellipse. And most of them we're going to start with are going to be centered at 0, 0, so H will be 0. This looks a lot like a circle, except for this. Instead of equaling the radius, we have different amounts in each direction. That equals 1. A is always the larger of the two, so this is a horizontal. A is always larger than B for an ellipse. This is going to be vertical. Again, the only thing that's changing is which one is A and B. And it doesn't really matter when you're looking at it, but it matters for some of the equations that we're going to do with this. Okay? So, I'm going to talk about key points on an ellipse. I'm going to draw another one here. The distance from the center, so center is going to be here right at 0, 0. This distance this one, it's longer on the x direction, so this is a horizontal. That's A. This distance right here is B. These points here, these aren't the greatest drawings. You can see a better ellipse if you look at a textbook. It's an 8.2 in yours. The reason we're not doing it out of the Precalc book here is it's too advanced for not having done it before. It just assumes you've done it. And so we're starting at the haven't done it before point. These are called co-vertices. These ones here are called vertices. So we have two axes. They go from the center to the vertices or the co-vertices. This is called the major axis. That's the longer one. And its length is 2a. This one is called the minor axis. Its length is 2b, because b is the distance from the center to the co-vertices. So it's 2b for the whole thing. Okay. The 2 points that we're equal distance from, these guys here, are called foci. This is where the A and B become important. Why did they show it here? I have it written in your packet. This is always true. C squared is always equal to A squared minus B squared. That's why A has to be the longer one. Let's put the foci on here in a different color. The foci here are green. The distance from the center to the foci is C. Okay. So let's do one of these and let's do an example. So what is the equation in standard form of an ellipse centered at the origin? Always important to start with your center. Most of them we're going to do are going to be centered at the origin. With one vertex at -6, because it's centered at the origin, I know the second vertex is 6, 0. They don't need to tell me that. It's just going to be there. And co-vertices, I'm going to call those CV, are -3, 0 and 3, 0. So I can quick throw together a graph. I'm going to label it to get to my points and no further. These are all ones. I don't feel like writing them on there, squishing it in. So I'll put my vertices and co-vertices on here, and I'll try to connect them with a semi-competent ellipse. So it asks me for what is the equation? Well, I know A here is 6. B, based on the distance from center to co-vertices, is 3. And H and K are 0. Standard form for an ellipse over 36. Because A is going in the horizontal direction, I'm going to put the A under the X. So the longer one, well, it's based on which direction you're going. Oh, I did my co-vertices backwards. It's not 0, 3, it's 3, 0. Or not -3, 0, it's 0, 3. And oops. Those are going in the Y direction, so those go under the Y. There we go. That's better. And it is always equal to 1. There's my equation. So this didn't ask me for this, but I want to find the foci. I know that C squared is A squared minus B squared. That is 27. So C equals square root of 27. I'm going to plot those on the graph. Foci, they must be on my major axis. Square root of 27 is going to be a little more than 5. So they're on my major axis. Since my major axis was horizontal, they're on the x-axis here. There's my foci. Okay, so we're going to do another one, but it's not going to start in standard form. Let's make that a little later. So I know standard form must equal 1. So I'll divide each side by 225. And then I've got to reduce these fractions. Hint, they'll reduce pretty easily. 225 does divide by 9 by 25. They're not giving you ones that they don't. And a lot of times it's 25 over 225 is 9. 9 over 225 is 25. I'm now in standard form. I know A is my longer one, so A squared is 25, and B squared is 9. This is a vertical ellipse. Going up and down 5. Again, there's no H in K, so it's centered at 0, 0. And each way 3. So I know my foci here are going to be along my major axis, which is in the y direction. And I know that my foci, let's do c squared, are c squared from the origin. That's 16, c equals 4. So they're going up and down 4. I give my coordinates 0, 4, and 0, -4 are my two foci. Okay. So, has anybody ever heard of a whispering gallery? A whispering gallery is based on echoes. And one of the cool properties that we talked about, a parabola reflecting all points coming straight down to the focus. Well, a ellipse will reflect all points coming from one foci to the other foci. So we get an ellipse, and a whispering gallery just has an elliptical ceiling, or really a three-dimensional ellipse. So that means if I talk from foci 1 in this direction, my sound will be reflected here. And the reason you can whisper and the sound will carry rather well is because it's all focused. It's not spreading out. Generally, your sound spreads out in 3 dimensions, kind of in like a spherical thing. Well, with the whispering gallery, it'll focus it and reflect it all the sound that's coming in a 3-dimensional space, all going out, will reflect to a single point, the other focus. So instead of being dispersed and losing it all dispersed energy, because sound is kind of an energy carrying out and it goes in all directions and you hear a little bit of it. That's why the further you get away, the harder it is because the sound travels there, but it's less concentrated. Well, the ellipse, the whispering gallery, focuses it all back to a single point, the other foci. Okay, so the application of this is just, they're going to tell me if an elliptical ceiling has a major axis of 120 and a minor axis of 72, how far apart are the foci? So, major axis, let's make that capitals, is 120. That means A is half of that, that's 60. We're going to use major axis as capital M and minor axis as little m. Minor axis is 72. That tells me B is 36. So how far apart are they? C squared is 60 squared minus 36 squared. And I need a calculator to do that. And then when I square root that, I get 48. So 48 is not the distance apart. 48 is half of the distance apart. 48 is distance from center to foci. So the distance apart is twice that, which is 96. Right. Okay. So we are going to talk about the eccentricity of an ellipse. Eccentricity has to do with how circular it is. And that is a very simple equation. Eccentricity, let's spell that for you, is simply equal to C divided by A. Okay, C will always be less than A. A is the length of the whole major axis, or half the major axis. And C is on the major axis, it's part of it. So this will always be a number less than 1. Okay, so calculating an eccentricity. The Earth's orbit has a semi-major axis, that's A, of 149.598 gigameters. Ellipses are very popular. They're generally planets orbit an ellipse. Actually, most orbits of anything are ellipses. And has an eccentricity of 0.0167. Says calculate and interpret B and C. So we know that E is 0.0167. We're going to actually have to calculate 0.167 equals C over A. We're going to have to calculate C first. And we get this for C. What does that indicate? The two foci are pretty close to the center of the orbit. In fact, they're very close to each other. We got 150 for A, and we're 2.45 for B. So, or for C. So here I've got, that means it's pretty circular. Okay, I got this like 149 here. Right, we'll just round that off. And C here is like 2.5. Those foci are very center. It's a very, the Earth's orbit is elliptical, but it's pretty close to a circle. To get B, I know C squared. C squared equals A squared minus B squared. 2.464 squared equals 149.598 squared minus B squared. Here's what I'm going to do to solve this. I'm going to subtract B squared from both sides and subtract 2.464 from both sides. So essentially, I'm going to swap those two. Or actually, I add B squared, I subtract 2.464 squared. And then I'm going to solve for B. And I get B is 149.578 gigameters. Somehow I have A wrong. Oh, I'm slightly off. I have a typo on A. So it's actually 577. I did a typo when I put it in my calculator. I did 147.598 instead of 149. So this is actually 2.49. That's 577. It's very close. It's a little bit skinnier. The Earth's orbit is a little skinnier on one side than the others. You don't really notice it in seasons because that's more about the changing of the direction of the sun.